Okay. Hello, everyone. Thank you, Giovanni. My name is Nicola Ruaro, and today I'll present our paper, SYMBEXCEL, Automated Analysis and Understanding of Malicious Excel4 Macros, which was developed as a collaboration in between UC Santa Barbara and VMware. Excel4 macros are a very old feature of Microsoft Excel, which was introduced more than 25 years ago as a precursor of VBA macros. Excel4 macros are extremely powerful as they can interact with the Windows API and therefore directly interact with the underlying operating system. For example, opening files, reading files, creating new files, or even executing shell commands or executing executable files. And for this reason, and because they are extremely intuitive and easy to program even without any programming experience, they are still commonly used for benign purposes. However, the same power and flexibility also makes them the perfect target for being abused for deploying malware to a target system. As a result, we have observed Excel4 macros being weaponized since at least 2013, with the recent spike of malicious usage in the last 2 years, with tens of thousands of samples submitted to VirusTotal every month, and an interesting and strong evolution in the obfuscation techniques. The typical infection flows in this kind of attacks starts with the delivery of an email. Once the target user downloads the Excel file and opens it in Excel, the Excel4 macro will be then executed and eventually show its malicious behavior, for example, by downloading a malicious executable and then executing it to infect the target system. The goal of our analysis at this point is to understand all the possible behaviors of such macro and to extract indicators of compromise, or IOCs, such as URLs, IPs, file names, etc., which you can later use for further analysis or forensics. The problem, however, is that these samples are heavily obfuscated, as you can see here in the slide, and the obfuscating such macros has therefore become an increasingly hard problem. In practice, malware authors use the functionality in Excel4 macros to implement obfuscation, which is typically implemented using the formula.fill function, for example, to concatenate multiple characters or substrings, as you can see in the example, and dynamically generate a payload which will be later executed. This type of code generation shows how we will need to evaluate the code as it is constructed and also how some ambiguity in between the code and data in the spreadsheet is introduced. And malware authors also implement environmental checks to test whether a sandbox is present or not, in particular by triggering some kind of user interaction, checking for the display size, or for the consistency of the system clock, for example. And all these techniques can be combined in order to introduce time dependency or environment dependency in the macro. So getting back to our example, you can see how this malware uses the day of the month in order to rotate some hard-coded integers that reside somewhere else in the macro and therefore dynamically generate the payload. Whenever this payload is executed on the incorrect day, it will then deobfuscate an invalid and non-functional payload. However, when we execute it on the correct day and only on that day, it will deobfuscate correctly and therefore infect the target system. So due to these analysis challenges, manually extracting Excel4 macros has become an extremely tedious and error-prone process that often requires a malware analyst to manually step through the macro cell after cell. And so the question is, can we automate this deobfuscation process in the presence of environmental dependency? But let me first introduce the basic components of an Excel4 macro, which are functions, formulas, and macros. A function is the smallest entity that provides some essential functionality in the Excel4 macro. For example, the alert function, or arithmetic instructions, or Boolean instructions. A formula is essentially the content of a cell, but more precisely, it's the invocation of a function with possibly nested invocation as an argument. A macro, finally, is the sequence of formulas that will be executed as a whole. At this point, the control and data flow in an Excel4 macro are rather intuitive. The entry point is an arbitrary cell in the spreadsheet from which the execution will start. Once we identify the entry point, the control flow will then be passed to the cell lying directly below the currently executing cell, and so on and so on. Some of these functions, for example, the formula and formula.fill function, allow to copy strings or concatenate characters in a target cell, therefore enabling data flow. Finally, some functions, such as the goto function, run, return, or even user-defined functions, allow to redirect the control flow to a target cell, which in this case is the cell B1, where the execution will continue, and finally the macro will terminate when hitting the halt instruction in the cell B2. Now that we understand how an Excel4 macro works, the basic idea behind SYMBEXCEL is that we can use symbolic execution in order to model all the possible execution paths in a macro while keeping the environment symbolic, which allows us to fork the execution whenever we hit a conditional instruction, and once we reach an interesting point in the execution, use a constraint solver such as E3 to generate to concretize the environment and therefore generate a valid configuration that we can use to execute the malware sample. The architecture of SYMBEXCEL is structured in three main components: the loader, the simulation manager, and the solver backend. The loader is the component which is in charge of parsing the Excel file and mapping it into memory. It will create an initial instance of the simulation manager, initialize its memory and its environment. The simulation manager then is essentially a simple state orchestrator which will keep track of all the execution states, and while stepping from one state to its successors, it will incrementally identify the formulas as they are being executed. The simulation manager will parse such formulas to generate an abstract syntax tree, or AST, and to identify all the functions invocations, and will then dispatch the execution to one or more of some function handlers. These handlers can then update the memory, access the environment, generate new constraints, or generate new branches or states. Every state has then its own copy of the memory, of the environment, and of the constraints. In the memory, you will see values such as the cell values, formulas, or cell information. The environment is what is used by the malware authors to identify to spot the presence of a sandbox. For example, values such as the window height or the OS version are initially unknown and different from target system to target system, and therefore, we associate each of these values with a symbolic variable, which leads us to the constraints, which are a characteristic of the malware execution. And for example, a constraint such as window height greater than 390 will be generated when we hit a conditional instruction and then propagated to successor states. We will now go through a simple example in order to make this all more clear. The entry point in this case is the cell A1, which will be executed, and the char instruction will write the value h to the memory of the cell A1. The get.workspace function in the cell A2 will then read the symbolic variable workspace 14 from the environment, which corresponds to the window height, and write its value into the memory. We then execute in the cell A3 a conditional instruction, which will write the value x or L to the cell A3, depending on whether the condition is true or false. In this case, the condition is symbolic, so we will fork the execution, generate two new states or branches, and then enrich such states with the correct constraints. We will then parse the formula in the cell A4 and write the result as a new symbolic expression in the cell A4. The formula.fill function in cell A5 will then concatenate the first 4 characters in memory and generate a second symbolic expression, a new symbolic expression, and write its value to the cell which is lying directly below the currently executing cell, the cell A6. So you notice how when we now step the execution, we are executing a formula that contains some symbolic values. And the only meaningful way to execute such formula is to try to concretize its value. We quickly realize, however, that one of the variables that are used in such expression is an unconstrained integer symbolic variable, which can have up to 2 to the power of 32 solutions. which is clearly infeasible to evaluate dynamically. So the question becomes, can we do better? And the answer is yes. We introduced various optimizations in order to make this concretization possible and feasible. For example, observers are intermediate variables that we introduce in order to hide and observe other sub-expressions in our symbolic executor. For example, in the expression in cell A4, we can wrap the Boolean sub-expression workspace 14 greater than 390 in a Boolean observer, which then allows us to reason more precisely on such expression and understand that it can have at most two solutions. We also introduce smart concretizations, and in other words, we use the Excel for grammar itself in order to filter the concretized results. For example, in the running example, we still have 6 possible concretizations. However, once we use the Excel for grammar to filter these results, we understand that most of them are invalid, and only one possible concretization can then be written to the cell A6 to continue with the execution. To evaluate our approach, we use a dataset composed of approximately 24,500 malicious XL4 macros, which have been detected by VMware using various techniques, including manual analysis, and then provided to us. Some of these samples, approximately 5,700, are publicly available, while the rest is private. We detect that a significant percentage of the samples show some kind of environment dependency or time dependency, which means that in order to analyze these samples, we will need some type of symbolic reasoning. We then evaluate SYMBEXCEL against the state-of-the-art concrete deobfuscator, XLM macro deobfuscator, on all the samples, showing that SYMBEXCEL can deobfuscate correctly almost double the samples than the state-of-the-art, and against the environment-dependent samples, showing that in this case, the pattern or the improvement is even more evident, with SYMBEXCEL deobfuscating more than 10 times the samples when compared to the state-of-the-art. As a practical example, we have observed some complex behavior being encoded in such macros. In this case, you can see a malware sample which uses multiple deobfuscation routines with multiple infection stages. And while the state-of-the-art can only deobfuscate correctly the infection stage 1 and infection stage 2, SYMBEXCEL can continue with the deobfuscation even when the environment dependency is introduced. The green nodes in the slide, in particular, represent formulas that are only deobfuscated correctly with the correct environment value. Similarly, the red node represent concretizations that are possible but not allowed under the XL4 grammar. Furthermore, thanks to our symbolic execution approach, even when the state-of-the-art cannot identify any malicious behavior, SYMBEXCEL can identify all the possible behaviors of the XL macro. In this example, SYMBEXCEL identifies 2 behaviors that are only displayed in 32-bit systems, and that in particular try to iteratively download a malicious executable file from different URLs and then execute such file. SYMBEXCEL also identifies a 3rd behavior, which is only displayed on 64-bit system, that will generate dynamically a VBS file right to the file system and then execute it in order to download a secondary payload, which is then executed in a different way. As a result, SYMBEXCEL can extract indicators of compromise that would otherwise be impossible to extract using the state-of-the-art. For example, the file names or URLs that you can see in the slide. We show that SYMBEXCEL can extract more URLs, file names, domains, and IPs, and provide a more in-depth discussion on such indicators of compromise in our paper. Finally, we performed the temporal analysis of the XL4 macros in our dataset. In particular, we observe an interesting evolution mainly in the triggering mechanisms, in the obfuscation, sandbox detection, and anti-analysis techniques. In summary, we study and classify such behaviors and show their evolution in the slide here. By correlating then these distinct behaviors with the antivirus labels or AV labels from VirusTotal, we can discover some interesting patterns. For example, you can see how the clusters 1, 2, and 3 all belong to the Z-loader families And from our analysis, they show a similar base behavior. Therefore, since they have some significant changes in the evasion techniques used, we can infer that these three clusters were developed and deployed in subsequence as waves of the Z-loader family, and in order to evade some analysis techniques that were introduced at the time. In conclusion, we can safely say that deobfuscating XL4 macros is still a hard problem, with many of the samples still having a very low detection rate in VirusTotal, and some of them still being undetected. SYMBEXCEL, however, can allow the analysis of samples that would otherwise be impossible to deobfuscate with the state of the art. Our code is public in the UCSB SecLab repository in GitHub. Please check it out. If you have any question, I'm happy to answer them, or please contact me at the email here in the slide. Thank you.
All right, we have time for some questions. Please walk up to the mic.
Yeah, I wanted to ask whether you needed to introduce any sort of path pruning heuristics, or whether the macros that you were trying to deobfuscate had simple enough control flow that that just didn't come into scope.
Yes. So as I was describing in the slides, an example of kind of path pruning that we introduce is in this smart concretization technique. In some ways, some kind of path pruning, since we try to identify formulas that would otherwise be impossible to execute and prune that path. Otherwise, symbolic execution can clearly explode. We can have path explosion. In practice, we didn't observe it in the current malware samples, so it was not necessary to introduce.
So you didn't have to resort to anything like cutting off paths after some fixed
Yes,
length? Or
that was not necessary yet.
Awesome. Very cool.
Hi, I was wondering how hard it would be for a malicious file to make you time out, such that you can't actually do the analysis. I'm assuming it would
I would
be very
expect
easy.
that to be very possible. And it, again, doesn't happen yet, but I can expect malware samples to introduce some loop or to try to make the symbolic execution like going path explosion and therefore timeout.
Thanks.
Very nice talk. I have a question also related to path pruning and also like timeout, because my question might be a little bit more initial, comparing to those questions. I just wonder, for this symbolic execution, and for example, Excel's malware cases, how bad is this path explosion problem? Is it really bad? Like we do need path pruning, or it's not that bad? Like have you checked like the comparison of no path pruning versus path pruning, and is it really necessary to do path pruning?
No, we didn't check. We didn't observe samples. I would guess that in the future it will be introduced, especially with this approach being released. I would expect samples to try to introduce ways to evade our approach, and we can then update the tool to try to identify paths that would be more important to explore first, or introduce some kind of path pruning.
Thank you.
I have one question. So do you know, are people still writing new such macros, so benign such new macros, or is it just old legacy code that people are still using in companies?
Of benign macros?
Yeah.
I don't know. We don't have a good data set of benign macros. So I cannot answer the question.
Because maybe it's time to disable those and to just whitelist the ones that are still around or something like that.
No, I can expect though people to still actively write such markers. As I was saying at the beginning of the talk, they are very easy to write. So even people that don't have any programming experience can pop up Excel and implement some kind of analysis that they need to do for the data. So I would expect these to be still used. Certainly legacy, but I would expect new markers to still be implemented and used.
All right, let's thank the speaker again.